We have these wonderful devices called operational amplifiers. These are readily available, inexpensive, almost magical devices. The internal workings of an operational amplifier are complex. However, to use them, we just need to understand their basic properties. So for now, we'll attribute the behavior of operational amplifiers to magical hobbits that live inside the devices. The hobbits are responsible for determining what components are around the operational amplifier and then making the pins of the operational amplifier behave appropriately. In the last video, we looked at the ideal model of an amplifier. We came to the conclusion that an operational amplifier behaved like an ideal amplifier if we used it under certain conditions. The details of those conditions will, for the most part, remain a mystery in this series, but that's alright, because right now all we need to be able to do is analyze and build simple operational amplifier circuits. This is an introduction after all. Let's begin by looking at a basic operational amplifier. Here's one that comes in an 8-pin DIP package. DIP stands for dual inline pin. There are many different types of operational amplifiers and they come in a variety of packages and shapes. I'm going to focus on the single op amp in an 8-pin dual inline pin package, mostly because these are the ones we use in the introductory laboratory projects most often. They fit perfectly on a breadboard and they are inexpensive for those wiring mistakes that happen from time to time. The 8-pin DIP package is laid out something like this. Sometimes there's an indentation in one of the corners. We number the pins so that we can easily identify them. This indentation is to indicate the location of pin 1. Incidentally, this is the context in which the phrase pin number is perfectly acceptable, because we are referring to pins. It's not like that annoying and redundant usage of the pin number that goes along with the equally annoying ATM machine. It's already in the acronym. PIN stands for Personal Identification Number. ATM stands for Automated Teller Machine. You don't need to say the last word twice. Sorry. Back to electronic. The indentation indicates the location of pin 1, and then we can find the numbers of the other pins by counting in a counterclockwise direction. Another form of the 8-pin DIP package is this. Instead of a little indentation in the upper left-hand corner, there is a semicircle taken out of the top of the package. Pin 1 is to the left of the indentation, and we count around counterclockwise to identify each of the pins. If we were to draw the circuit symbol for the operational amplifier inside the package, it would involve pins 2, 3, and 6. These are not the only pins important to the operation of the device, but they are the ones that deal with the signal we want to amplify. I'll briefly discuss the purpose of the other pins. Pin 1 can be several different things, although very often it is something called offset null. This pin is sometimes used in conjunction with another pin in the package to balance out some imperfections that might exist inside some operational amplifiers. For operational amplifiers that fall into this class, pin 2 is called the inverting input. The operational amplifier is a differential amplifier, so it has 2 inputs. To ensure an operational amplifier works correctly, we have to make sure we keep track of the inverting and non-inverting inputs. Pin 3 is the non-inverting terminal. Pin 4 is the negative DC power supply. The operational amplifier does not create amplification out of nothing. We have to supply power. Conservation of energy always holds true. The power it needs to amplify signals comes from the DC power supplies. Pin 5 can be another offset null connection, or sometimes it has no connection. Pin 6 is the output of the operational amplifier. Pin 7 is the positive DC power supply, and pin 8 is often not connected, although sometimes it can be an offset null pin, depending on how pins 1 and 5 are used. I should again point out that there are a lot of different configurations for operational amplifier integrated circuits, and you should always refer to the datasheet for your device before wiring it into a circuit. A common circuit symbol used for the operational amplifier is this. We have an inverting input, a non-inverting input, an output, a negative DC power supply, and a positive DC power supply. The 2 power supply pins provide energy to the circuit that's necessary for it to amplify signals. However, when we are analyzing operational amplifier circuits, we often assume the power supply and ignore these voltages in our analysis. We're not truly ignoring these pins, as they determine the behavior of the operational amplifier. Once the power supplies are set, the amplifying characteristics of the op amp are already determined. So we just use the properties that are determined rather than dealing directly with the power supply voltages again. So what are the properties that are determined? We'll start at the input terminals. One property the input terminals have is an infinite input resistance. Because of that, no current enters either of the input terminals. There's also no voltage difference between the input pins. We can attribute that to the fact that there's no current into the input pins, if that makes sense to us, but it's probably more appropriate to attribute it to the infinite gain of the amplifier. At the output, we assume there's no resistance. That, coupled with the dependent source we talked about last time, gives us the property that the output current of the operational amplifier will be whatever it needs to be to make the circuit work. Now that we have those properties, it's time to analyze some circuits. Our general approach to analyzing operational amplifier circuits will be to assert the properties of the operational amplifier, and then we will determine the voltage at the non-inverting terminal. From the properties of the operational amplifier, this will give us the voltage at the inverting terminal, and then we can write a node equation at the inverting terminal. So we begin analyzing the circuit by asserting the properties of an ideal op-amp. No current enters the input terminals. There's no voltage difference between the inputs, and at the output, we have an unknown current that can go in either direction. That means we cannot write a node equation at the output terminal that will help us solve this circuit. Kirchhoff's current law will still hold, but we will not be able to determine that current until all the other currents in the circuit are known. So we start at the non-inverting terminal. This terminal is connected to ground, so the voltage there is 0 volts. Because there's no difference in potential between the input pins, the inverting terminal will be at 0 volts as well. We can then choose directions for the currents through the resistors, ignoring the load resistor because it does not contribute to the solution, and at the inverting terminal proceed to write a node equation. Multiplying through this equation by a negative RF gives us that the output voltage will be the negative ratio of RF and RI. A few notes here. The most obvious is that we have a clear way to get a predefined gain out of this amplifier circuit. It is simply a ratio of resistors. The output does have a negative sign, but that's usually not important. For example, if this were an audio amplifier and we were listening to the output, the negative sign would be the equivalent of saying our sound is upside down. Another note is that the output of the operational amplifier is connected through a resistor back to the input of the operational amplifier. This is called feedback. Specifically, this is called negative feedback because the output connects to the inverting terminal of the operational amplifier. For reasons I won't go into, this is necessary for the proper behavior of the circuit. The fact that the resistor is providing feedback is why we call it R sub F. F stands for feedback. This configuration is called an inverting amplifier because the output is amplified, however it is negative, so a time varying signal will be upside down compared to the input. Another side note, though we are going through several different configurations right now, all of which have predefined outputs, I strongly encourage you not to memorize the equations for the output voltage. It is way too easy for our brains to trick us into thinking we're seeing a configuration that we are not and applying an incorrect equation. If you're going to memorize anything, memorize the procedure. The procedure will work every time. Here's another configuration for an operational amplifier circuit. All that has changed from the previous one is that the input signal has been moved. Again, we will start by asserting the properties of the op-amp. No current enters the input terminals, and there is no voltage difference between the input terminals. The output current is unknown. Now we can proceed by determining the voltage at the non-inverting terminal. Since there is a voltage supply connected to it, and the other end of the voltage supply is connected to ground, the non-inverting terminal will be at Vin. This means that the inverting terminal will also be at Vin. After choosing directions for the current through the resistors, we can write a node equation. Multiplying through by a negative RF and gathering terms results in this equation. Factoring out Vin gives us the output voltage in terms of the input voltage and the resistances. In this circuit, our gain is a ratio of the feedback resistor and the input resistor plus 1. This amplifier does not invert the signal, so we call it a non-inverting amplifier. Here's the same circuit with the exception that a resistance has been added that might be associated with a source. We will analyze this circuit with the same exact procedure. Asserting the properties of the operational amplifier, we know that no current enters the input terminals. There is no voltage difference between the input terminals, and the output current can be anything. The source Vin is connected to ground so that this terminal will be at a voltage of Vin. Since no current enters the input terminals of the operational amplifier, no current will go through our sig. If no current goes through the resistor, there is no voltage change across the resistor. So the voltage at the non-inverting terminal will be Vin, as will the voltage at the inverting terminal. At this point, the same analysis as the previous example applies, and we get the same output voltage. The important thing to note here is that the output is independent of the resistance of the source. A little discussion here. We have two operational amplifier circuit configurations. We have an inverting amplifier configuration and a non-inverting amplifier configuration. From our understanding at this point, the non-inverting amplifier, all other things being equal, has a higher voltage gain for the same resistors. It does not invert the signal, and we can ignore the resistance associated with the source. If we look at the output voltage of the inverting amplifier configuration, it's pretty easy to see that a source resistance is going to negatively affect the gain of our amplifier. So I remember thinking at this point when I was learning about these, why would we ever use the inverting amplifier configuration? Unfortunately, that discussion's beyond the scope of this series. Suffice it to say, we're making ideal operational amplifier assumptions here. There are other effects that come into play. One of these effects is that there's a limitation on the ratio of resistors we can use. If we try to use a resistor ratio of 1,000,000 to 1, the circuit will not work. For now, let me just tell you that in the inverting configuration, we can use a larger ratio of resistors, so the circuit is capable of more voltage gain. Hobbits are a little bit backwards, and they're willing to work a little harder in the inverting configuration. Here's another special case of the non-inverting amplifier. We have simply replaced the feedback resistor with a wire and removed the other resistor. The analysis begins the same way with the properties of the op-amp. Our voltage source sets this node at Vn. Because there's no current through the source resistor, there is no voltage change across the resistor, so the non-inverting terminal is at Vn. That means the inverting terminal is also at Vn. Since that terminal is connected to the output voltage is also Vn. So the output voltage is exactly what the input voltage is. This circuit is called a voltage follower. Why would we bother with such a circuit? The answer is quite simple. Without any gain, this circuit does not have the disadvantages of the non-inverting amplifier, but it still eliminates the effect of the source resistance. Since many sources have a lot of resistance associated with them, this circuit can be used as a buffer to reduce the effect of that source resistance. Now let's go back to the inverting configuration. However, this time let's attach two sources to it. Beginning with the properties of the operational amplifier, no current enters the input terminals and there's no voltage difference between the input terminals. And the output current can be anything. We will determine the voltage at the non-inverting input, which in turn tells us the voltage at the inverting input. After choosing directions for the currents through our resistors, we can write a node equation. Multiplying through the equation by a negative RF, we get the output is a weighted sum of the inputs. If R1 and R2 are equal, the circuit will simply amplify the sum of V1 and V2. We might also note that if we were to add another source, say V3 at the input, that term would simply add to the output in the same way. The circuit could be used to mix signals together. If we were to make the resistors R1, R2, and R3 into variable resistors, we would have the beginnings of a basic soundboard because we would be able to add the signals together in different ratios. One final analysis for today. We'll apply the same procedure to this circuit. The properties of the operational amplifier are that no current enters the input terminals and there's no difference in voltage between the input terminals, and the output current can be anything. Since no current enters the non-inverting terminal, the resistors R3 and R4 can be thought of as in series because the same current will go through each of them. So we can determine the voltage of the non-inverting terminal using voltage division. This will also be the voltage at the inverting terminal, and after choosing directions for the currents through R1 and R2, we can write a node equation at the inverting terminal. Multiplying through by a negative R2 and gathering terms results in this equation. Remembering that we also have an expression for the voltage at the non-inverting terminal, we can combine these two equations together and get an expression for the output voltage. This equation is more complicated than any of the other ones we've come across so far today, so let's see if we can simplify it. After making a slight change to the expression, if we apply the condition that R1 and R2 must be equal, and that R3 and R4 must be equal, the output voltage simplifies to the difference of the input voltages. So when we put these constraints on the values of the resistors, this configuration is a difference amplifier. Well, actually it's a difference amplifier even without these constraints. However, it's much easier to see that with these constraints. So there we have some of the basic configurations of operational amplifier circuits. We have an inverting amplifier, a non-inverting amplifier, a summing amplifier, and a difference amplifier. There are also a couple of special cases mixed in, and we developed equations for the output for each of these configurations. I do want to stress again that it's much more beneficial to remember the procedure for the analysis than to remember the equations for the output. The procedure is this: assert the properties of an ideal operational amplifier. Determine the voltage at the non-inverting input terminal. Using the same voltage at the inverting terminal, write a node equation at the inverting terminal. Then simply solve whatever equations we have at that point. That's all there is to analyzing circuits that have operational amplifiers in them, at least when we assume they are ideal. That's all I have for you today. Thanks for watching. Go out and make it a great one.